I'm Katie Fenn, and I'm going to be talking to you today about memory management and all the stuff that JavaScript does behind the scenes. So I'm Katie. I used to work at NPM. I now work for a company called Monzo. And if you've been playing Sega Rally this weekend, you also better know me as Kaz as well. I currently have the high score. So you can follow me on Twitter at Katie_Fenn. And just in case videos or animations on really big screens make you feel sick or uncomfortable, a content warning will appear just on the slide before they occur. So memory is fundamentally important to everything that we do in programming and computing. It's a finite resource. Like we don't have an API for adding more memory to our customers' computers, so we can only use it and reuse it. We've got to be good shepherds of what we're given. And as devices are given more and more memory as technology increases, our apps discover more and more creative ways of using it up again, as we can see with the history of operating systems. In the last 10 years, there's been a big change in the way that our sites are designed. Smartphones are now the most popular way of browsing the web. And this is just the high-tech tip of the iceberg. High-tech iPhones have lots and lots of memory, might have 4 GB of memory, but older devices and cheaper devices have a lot less. And we're often told that memory is really important. In fact, I've just told you that memory is really important. But the truth is that JavaScript does an awful lot for us. It does a really remarkable job of managing memory. I decided to look up in my copy of JavaScript, the Definitive Guide, a book that is that thick. I looked up in the index, and I tried to find instances where memory is mentioned. In fact, it's mentioned on just one page. In fact, it's mentioned in just one paragraph. It says, the programmer never needs to worry about deallocation of objects. The interpreter automatically reclaims memory. So how does JavaScript do this? Well, the inspiration for this talk is taking you behind the scenes so you can see how. Before we can answer that, let's have a look at what memory actually is. This is memory. This is what it looks like inside our computer. It's the little black chips that you can see on the daughter boards that slot into our motherboards. These are called DIMMs. And they are what we call RAM, random access memory. The reason we still use it is because it's lightning fast at reading and writing data. It's much faster than reading and writing data to the disk. Browsers allocate memory on our behalf, and the areas of memory are called heaps. When our page loads in the browser, our JavaScript creates variables, and the heap grows. And this process is called allocation. When our JavaScript objects are discarded, or we navigate away to other pages, the heap shrinks, and memory is deallocated. JavaScript allocates memory on our behalf when we declare variables. And once variables are declared, we can start assigning values to it. This is the equal sign, or to give it its proper name, the assignment operator. It's used to assign values to memory. In fact, all these operators assign memory in some ways, except some decrement memory, some decrement values, some increment values. They all do different things, but they all allocate memory. They all work by assigning a value on the right to an address that's described by a variable name on the left. So that's how memory is allocated in JavaScript. What about deallocation? Well, JavaScript uses scopes to deallocate memory. If the heap is a farm, then the scope is a field. Scopes break memory up like little invisible force fields around our code. And they allow us to reuse variable names and protect variables from other functions. Can you imagine if we had a function in one part of our code that's overwriting the memory in another part of the code? It would just be chaos. So we have scopes to break memory up to make it more manageable. So when a program flow enters a new block that we can see here, so a function is called, a new scope is created to allocate memory for variables. In JavaScript, scopes capture variables and values from outside to be used inside the scope. And when a function has run its course, its scope ends. So all these variables A, B, and C are only used in these functions. When the functions are called, the scope ends, and any variables that are used in that scope that are not needed anymore, and their memory can be reclaimed. Variables are only retained as long as their parent scope exists. And understanding this is the key to understanding how JavaScript manages memory. This process that JavaScript uses is called garbage collection. So that's how you control memory in JavaScript on the surface. Let's start going behind the scenes to see how JavaScript works. JavaScript belongs to a family of languages called garbage-collected languages. And it's not the only one. Other languages that you might have heard of, PHP, Java, Python, all these are also garbage-collected languages. But what it means is that JavaScript does a lot of work so that you don't have to. The easiest way to explain what garbage collection is to contrast it with a different language that uses manual memory management. This is a line of C, and this is allocating memory for an array of 10 integer items for 10 numbers. C is the language that's used to make many software tools, including lots of our browsers. And it gives you a lot of authority over system resources like memory. So if you want to declare an array of 10 items of 10 integers, you can use the malloc function. Memory is freed again using the free function. Now, this is an awful lot of control, but can you imagine doing this every time you needed to use an array in JavaScript? It would take you forever to write a website. So that's why we have garbage collection to take care of all this for us. Now, the following slides demonstrate how a garbage collector works, but specifically they demonstrate how V8's garbage collection works. Firefox garbage collector also uses very similar concepts, but I used lots of resources from the V8 team. So the heap is organized into a generational layout, and this divides memory into areas called the young generation and the old generation. This optimizes it for data that varies in terms of its lifetime, for young data that's short-lived and old data that is very long-lived. The young generation is optimized for short-lived data, and it's divided into two semispaces, 16 binary megabytes big. When a semispace fills up with data, a garbage collection begins. V8 pauses the JavaScript execution, which is shown by the red background, and it surveys the young generation. Objects are traced for their accessibility from the global object or from the call stack. Any objects that are still accessible, so their scope is still alive, is considered alive, and anything else is considered dead. Alive objects are marked and then copied to the second semispace. The memory in the first semispace is then discarded and overwritten, and this process begins again. This process is incremental in V8, so it breaks it up into bite-sized chunks so that your JavaScript can keep running and your application isn't locked up. To make sure the main JavaScript thread is running, it breaks it up just like we do in our code. We don't try and lock up the main thread. This is really important for application performance. So when the first semispace fills up, garbage collection begins again. This process begins all over again. Objects are traced for their accessibility. Alive objects are marked and copied. And objects that survived one garbage collection already are then moved to the old generation. The old generation is designed for longer-lived data. So this process is called scavenging, and it's responsibility of the minor garbage collector. Now, when I said that Chrome has a garbage collector, what I really mean is it has two garbage collectors. Scavenging is the responsibility of the minor garbage collector. And it's really, really efficient at what it does, thanks to the generational hypothesis. What this means is that most of the objects that we create in JavaScript are short-lived. They're temporary. We create them, we use them, we discard them. And this means that this process, scavenging, is really, really efficient. So that's the role of the minor garbage collector. There is another garbage collector for managing longer-lived objects. Now, it frees objects from across the whole heap, but we're going to focus on the old generation now. The old generation is designed for longer-lived objects, things like settings, things in the global scope, things that live forever as long as our web page is open. And this works similar to the minor garbage collector. Objects are traced for their accessibility. Alive objects are marked. This process is called marking. This happens concurrently with your JavaScript, so your application can keep running while this process is going on. This is part of the goal of Chrome's new Orinoco garbage collector, which tries to make as much of this process as concurrent as possible. Dead objects are added to a free list. This is like an index of chunks of memory that can be written to. So when you create new variables, Chrome V8 looks up for free pieces of memory that it can write to in this free list. This process is called sweeping, and it happens off the main thread again, so your JavaScript can run concurrently. Next, V8 pauses JavaScript execution, and then it starts compacting memory. So bits of memory that are being used are rearranged to make it more efficient. It's a lot like defragmenting a disk in Windows 95 or Windows XP, if you remember doing that. Surviving objects are moved closer together, and this is designed to make reading and writing to memory more efficient. This process is called compacting. It takes about 10 milliseconds, and it can only happen while your JavaScript is paused, because all those references to those chunks of memory are all being moved around and rewritten. So the mark and compact garbage collection that we've just seen is the domain of the major garbage collector. It has a couple of optimizations for when most of your data is long-lived, so it's passing straight through the young generation to the old generation. It's called pre-tenuring. And it also falls back to an incremental garbage collection when the concurrent version isn't working efficiently enough. So that's how it works behind the scenes. What happens when we actually have problems in memory that are manifesting in our web apps? What does it look like? Well, there's two main classes of problems, and they're called memory bloat and memory leaks. So how do you know that you have a problem? Well, usually when it looks like this, your Chrome tab crashes. This could be unresponsive JavaScript, but it could also be the result of a memory leak that is just running away, and the garbage collector is not being able to do its job. On Safari and iOS, when I have a web app open, I'm trying to scroll up and down, and it's slowing down, it's not animating, I can't scroll, and it just locks up, and eventually it just says, I can't do it anymore. You get a little band at the top that says, this page was reloaded because there was a problem. My video isn't working there, but never mind. OK, so this is called memory bloat, and it's when we make our websites too unnecessarily large and dense for what their purpose is. So HTML, CSS, images, fonts, videos, JavaScript, all this is stored in memory. And if you're using too much of it to serve your website's purpose, this is called memory bloat. You can find out about memory bloat by opening a Chrome Task Manager and finding out how much memory your tabs are using. And it also breaks down the memory that's used by your JavaScript as well, so you can figure out whether you have a problem with JavaScript or whether you're just bloating memory with images and HTML and so on. A baseline consumption for Hello World is about 100 megabytes. And this is the overhead of any given website in Chrome. The memory is, this is just the memory that's needed just to show the text on screen and to provide JavaScript's basic APIs. But a really crowded page consuming about 200 megabytes of memory might not cause an issue on a desktop like this, which has 16 gigabytes of memory. But if you have a phone that has a fraction of that, it might start causing problems. So make sure you optimize your images and the content for different platforms and test them out on real devices. The other class of problem that we see is memory leaks. And this is when JavaScript code continually adds more and more data to the heap than it discards. Leaks are caused by code mistakes which prevent data from dying off. In other words, if this is your data, this is you realizing it's still alive and clogging up your app. So now it's time for a live demo. I'm going to try and trigger memory leaks inside my slide deck for fun. Let's see if this is going to work. OK. There we go. Right. So this is running in a web browser, and I have this code running whenever I click this button. And we can see here that it creates a global variable. This variable is not bound to this function, which means it becomes a global variable. That means that it's going to live for as long as this tab is open or until we refresh it. So this is a really, really good way of creating a memory leak. So what I'm going to do is I'm going to open Chrome DevTools. I'm going to try and make it a bit bigger. And I've opened the performance monitor. The performance monitor can be found in this little menu under More Tools. Come on. There we go. And it shows you in real time things like the CPU usage, the JavaScript heap size, and the amount of DOM nodes that are shown on the page. So if I click this button, we should see the heap size jump in size. So it's about 20 megabytes at the moment. I'm going to click it, and it's going to swell to almost 400 megabytes. This is a really, really bad function. I'm going to go and try and find the memory tab, and it has a wonderful little button here called Collect Garbage. This forces a garbage collection, so we can see whether our data is actually being cleared whenever a garbage collection happens. I'm going to click it, and we're not making any difference to the heap size. So what I'm going to do, I'm going to refresh the page. We can immediately see the heap size shrink back down to its normal level. And I'm going to go to a fixed version. This fixed version, you can see it has the let keyword. So this variable is now bound to this scope that is created by this function. So as soon as this function is called and it finishes being called, we should see the heap size shrink. So I'm going to click the button again. The heap is going to grow. And now I'm going to click the Collect Garbage button, and it should shrink again. There we go. So the moral of this story is to always make sure you're binding your variables and declaring them inside a scope. The garbage collector is really, really efficient when most of our variables are temporary, and it's really good at clearing them. So make sure you're always declaring them in a scope that will be discarded. Next, timers. When we use a timer, when we create a timer, we use the set interval function or the set timer function, and we pass in a callback. That callback creates a scope that is alive as long as that timer is needed, because all the variables that are accessible by it need to remain alive. So if I start the timer, we should see every time it ticks, the heap size grow. And we can see it ticking, ticking, and it's growing in size every time. The only way we can stop it from growing is by making sure that we clear this timer by calling clear interval. So I'm going to stop the timer. We should see the heap size stop growing, and I'm going to try and run a garbage collection. We should see it shrink. So make sure you get rid of any timers that you're not using anymore. Another time that we create callbacks that create scopes that stay alive is event handlers. So we create an event handler, we pass in the callback function, and as long as that event handler is needed, that scope stays alive. So I'm going to try and click on this button, which calls the event handler, and every time I click it, it grows. I'm going to show you that this is actually happening in real time. Ah, come on. There we go. It's growing every time I click it. So if I try and collect garbage, we should see the heap size stay as it is. What we need to do is we need to get rid of that event handler. And then we should see, when we run a garbage collection, the heap size shrink. So what I'm going to do is I'm going to type button.onClick equals empty string. That gets rid of that callback. And then if I create run a garbage collection, it should shrink. So make sure you discard any event handlers that you're not using anymore. There we go. OK, so in summary, memory is a finite resource. We can't add more memory to our customers' machines. We can only use it, discard it, and then reuse it. We have to be good shepherds of what is given to us because we can't get any more. JavaScript does a lot of work to manage memory on our behalf that other languages have to do manually. The garbage collector frees memory for us that's not being used. Memory bloat is when websites that are unnecessarily large for their purpose. And memory leaks is when unused memory is not freed again. Finally, use DevTools to confirm the problems that you have. They're your friend. They have lots of really, really good tools to help you debug and fix memory leaks. So thank you very much. There's a link to my slides in the bottom there. It's all on Twitter.